All right, what if we have a sums of definite integrals? Well, because definite integrals are defined as limits of sums of rectangles, the following property applies, the sum property of integrals. So if we have the integral from a to c of f of x dx, we can break that up into the integral from a to b of f of x dx plus the integral from b to c of f of x dx, where b is some point in between the two. And why this works is because we might have something that looks like this example. So what we want to do is we want to find the definite integral of the function f in this figure from -1 to 6. Okay, well, it's in two regions. So what we can do is we can take the integral from -1 to 2, and when we do that, we find that's equal to 54. Then we can take the integral from 2 to 6, and when we do that, we find it's 128. And then basically we can say, okay, well, the integral from a -1 to a 6 is the sum of those two. So 54 plus 128 is equal to 182. So we split it into two integrals. We found both of those because it was, easy to do. And then we were able just to add those values together to get our final value. So that's how the sum property of integrals works. Now, what about definite integrals as areas? So for a function that's non-negative, so such as this one, it's non-negative, it's always above the horizontal axis from a to b, then the integral from a to b f of x dx is the area of the region between f and the x-axis from a to b. So again, so it's just that blue area right here. Now, what if we have a negative part? So if it's going below that x-axis. So here, the integral from a to b is going to be the negative area of the region between, f of a and f of b, and between that and the x-axis. So it's going to be a negative value. So we can see it's a negative integral from a to b of f of x dx. Okay, so it's going to be a negative value. Now, definite integrals as signed areas. So for a general function f defined over an interval from a to b, that integral from a to b of f of x dx is the sum of the signed areas of the regions between f and our x-axis from a to b. So you might have some above, you might have some below. And so what you're going to do is you're going to take all of them as the positive areas, and you're going to take the positives minus the negatives. So you're going to take all the sums up here minus all the sums down here, and that will give you your total area. Okay, and it'll give you a signed area. So if the area down here is bigger, it's going to be a smaller number minus a larger number, so you're going to have a negative value there. Now, the total area of regions defined by f and the x-axis from a to b is calculated by, and what we're going to do is we're going to partition the interval. So you see our function here, it's some quadratic, and if we're looking between it and x-axis, well, here we have a positive value. But here, because we're below, that's going to be a negative value. And then back over here, we're at a positive value. So what we need to do is we need to find these zeros so we can then say, okay, we're going to go from this point to this point, and then we're going to go from this point to this point and add those two together. That's going to be our positives. And then we'll take the integral from this point to this point, and that's going to be the area that's negative, and we'll take the positives and subtract off the negative area, or if we have it as a signed area, we can take and add all of them together as signed areas. So depending on how you want to look at it, you can do that. All right, so so here what we're going to do basically is we're taking the x squared plus x or minus 6, and we're going from -5 to 5. Okay, so all the way over here, the whole region. And so first we're going to go from -5 to 3. We're going to get that area. And then it says, well, let's subtract off the area here. Well, that area here is going to be a negative, and so that's going to give us a negative. So we're looking for the total area. We don't care about, signs in this case. So we're taking this and then minus and the minus, so it's plus that. And then the area from here to here, and it's going to be plus that. So that will give us the total area that's in blue. Now, again, if we wanted the area of positives and then subtract off the negatives, it's just going to be a sum of all of them. So it'll be that plus that plus that. And because that's going to be a negative, then it's going to basically subtract it off. And then you can see, is it more positive above or more negative below? So it kind of depends on what you're doing on how this is going to work. So what if we have definite integrals and piecewise defined functions? Well, it's necessary to treat that definite integral as the sum of the parts. So if we have a three-piece piecewise, you're going to have three integrals. If you have a two, you have two integrals. And so it's going to be a little bit more work depending on how big your piecewise functions are. So let's kind of look at this example here. Here we have the rate of change in popularity of a recent US president before and after his inauguration. Can be modeled as follows. So we have three pieces. So it's going to be this between negative 1.9 and 0.7, and it's going to be this when it's between 0.7 and 3.6, and it's going to be this when 3.6 to 12. So P prime is a measure of percentage points per month, and M is the number of months since January 1st of the inaugural year. So inauguration day is at 0.7. So that's kind of what that is. So, you know, when he got elected to when he actually took office, basically, it looks like. All right, so use the definite integral notation to write a formula for determining the net change in the president's popularity between his election, M equals negative 1.9, and 1 year after his election, M is equal to 10.1. Illustrate the net change as regions bounded by the graph of P prime. Then write an expression for P, a piecewise defined general antiderivative function for P prime. Sketch a graph of the president's popularity given his popularity rating was approximately 53% on election day. And then C, determine the net change in the president's popularity during the first 12 months after his election. Interpret each piece of the sum of definite integrals in terms of the change in the president's popularity. All right, so first things first, we have to define our antiderivative. So the net change in the president's popularity can be expressed as the sum of three different integrals. So again, we have to break it into those three pieces. So we're going to take the integral of this between here and here, the integral of this between here and here, and the integral of this between here and here. And that's what we've written. From here to here, we're taking that integral. From here to here, we're taking this one. And from here, we're going and doing that integral. Okay, so that's all I asked for. Just represent it as different integrals. Okay. Now, if we look at it, this is how it's going to kind of look on our thing. So, you know, we have the first lines going like this. The next line is coming up like this. And then the next one is kind of, what was it again? The 13.4 over M. So it kind of looks like that kind of function, okay? And so we're going from each of the pieces, and that's what it looks like. And so we have to go from the curve to the horizontal axis, whether it's on the top or the bottom, all right? Now, so the general antiderivative is basically what? Well, we're going to take the antiderivatives, and so it's going to be, you know, 2.6 m squared over 2, so it's going to be 1.3 m squared plus 3.8 m plus c1 between here, and same thing. So we're just taking each of these antiderivatives, and so we get piecewise antiderivative, and again, it's just a general because we have our c's, okay? Now here, P is measured in percentage points and M is the number of months since January 1st of the inaugural year. And this shows here a graph of P, assuming the starting point of P is negative 1.9 at 53%, which is what they told us in our problem. Okay, so it's going to start here. Then we just kind of follow from there and just kind of go through our motions of, okay, from here to here we get this, from here to here we get this, from here to here we did this. And that's going to be our graph. All right, so calculating the sum of the definite integrals in part A. So if we calculate the sum of those, we're going to, you know, actually do the calculation in our calculator and get a number. So we get 13.936, and then plus, and this one ends up being a negative 3.944, which, you know, that's what happens here. And then plus our here, we have a negative 13.4 over m. So when we do that, it's going to be negative as well. And so that gives us that. And again, this piece here is going to be positive, but this piece is negative and bigger. And so it's going to be more negative than it is positive. And so overall, he lost 3.831 percentage points. Okay. And so that's what it says. You know, the president's popularity decreased approximately 3.8 percentage points during the first 12 months after his election. And as president-elect, his popularity rose approximately 13.9 percentage points. During the first 3 months in office, his popularity had a net decrease of 3.9 percentage points. And that's from here. And then in the next part, he lost 13.8 percentage points, basically. Okay. So that's how it all kind of tied in and combines, you know, taking antiderivatives of that piecewise function. All right, let's stop there.